So it's my pleasure to introduce colleague, collaborator, and friend Han-Bom Moon, who's gonna talk about point configurations, phylogenetic trees, and dissimilarity maps.
Okay, well, first of all, thank you for the invitation. And thank you for coming to this talk, where this is already almost the end of the semester. So everybody want to enjoy the well-deserved time with their family, but thank you for coming here. So today I'm gonna give a talk about my recent joint work with Alessio Caminata, Noah Giansiracusa, and Luca Schaffler. All of them are here. Thank you. So then the topic is point configurations, phylogenetic trees, and dissimilarity maps. Okay. So for some impatient audience, so let me start with the main statement of the main theorem. So the main theorem is really, in some sense, a very basic one. So we want to understand the defining equation of some tropical variety. So here is the statement. So let's fix two integer parameters n and r. Then the weighted R dissimilarity map, of course, I'm going to explain the definition later. This map embeds the well-known space of phylogenetic trees Tn as a tropical subvariety Trn in R to the n choose R. The image has very interesting interpretation as a tropicalization of some moduli space, which is the tropicalization of the variety of point configurations lying on a rational normal curve. And moreover, when we take a vector W in R to the n choose R, then we can determine whether the vector W is in the tropical variety or not by using finitely many algebraic conditions, three-term Flick relations, and linear equations from cube. Well, I know that I need to explain a lot of different notations, but I'm gonna do that. So this is the result of our two joint papers. The first one is in 2018, and the second one is on arXiv. Okay, so let me start from some background. So I really prefer to start from very old results. So let me start from tree matrix theorem. Okay, so in this talk, what is a matrix tree? Matrix tree is a tree graph. And I will assume that every time all tree graphs have n leaves, which are indexed by integers from 1 to n. And there is no vertices of degree 2. And we are going to assume that each edge, E, has a positive length L of E. So in this picture now, you can see that these blue numbers are leaves, and we have purple numbers, which denote the length of each edge. Okay. This matrix tree is probably studied by non-math people because it can be understood as phylogenetic trees in biology. Well, in biology, if you have several species, then we know that by evolution, these species were branched out from a single species. Then where we want to understand their relative distance by describing the tree diagram. So this tree diagram means here we have the original species, their taxa, the DNA branched out, and then we can make different species, and so on and so on. So we can try to understand the relation, the distance between many species by drawing this tree diagram. And this tree diagram can be naturally understood as an example of a matrix tree. Okay. All right. So whenever we have such a matrix tree, then we can define a tree matrix. So here is the idea. For each pair ij of vertices, then we can define the distance between two vertices by taking the path start from one vertex I to another vertex, and add all of the length of the edges on the path. So here is one example. We have two vertices 1 and 5. Then we can draw a unique path from 1 to 5 and add all of the edge lengths on the path. Then this is the distance between 1 and 5, d1, 5. Okay, then we can compute that this is 3 plus 2 plus 4 plus 1, which is 10. Well, we can do the same thing for every pair of vertices. Then we can collect many numbers, and this is indeed a vector in R to the n choose 2. Then one can easily check that it defined a matrix on the finite set of leaves. So then, and this matrix is called the tree matrix because of the obvious reason.
So that long vector in the example, Dij,
yeah.
is that a matrix, or is that meant to be a matrix?
It is a matrix. Well, you know, if we have a finite set, then to describe a matrix on the finite set, we need to define the distance between 2 points, right?
No, yeah, no, I understand that. I just thought it would be in a matrix form rather than a one-dimensional.
Yeah, of course, you can describe it by using a symmetric n by n matrix.
Oh, okay, I see. Okay, never mind.
So this example came from this tree. Well, hopefully there is no computational mistake. I'm not sure. Okay, so this is one example, one way to define a matrix on a finite set of n points. So this is called a tree matrix. But of course, this is not the only way to define a matrix on a finite set. So here are some related questions. So now, instead of starting from a tree, so let's start from a vector in R to the n choose 2. Suppose that this vector provides a matrix on the finite set. Then now the first question is the matrix came from a tree matrix? In other words, can we find a matrix tree such that the distance tree matrix coming from the graph is equal to this matrix W? This is a very natural question. And where one can ask, is there any easy criteria? So can we test the question by using finitely many, for instance, algebraic questions? This is also very natural question. And another possible question is, suppose that it came from a tree matrix, then is the tree G is unique or not? This question is in particular very important in phylogenetic tree in computational biology, because this question is in some sense equal to the question asking, can we reconstruct the phylogenetic tree uniquely from the distance information of n DNA, n taxa? Okay. And where furthermore, we can ask some more practical questions like, well, if we can find a unique tree, then can we find the tree G effectively? This is another question. Is there any? Okay, so there was a question on the chat. Does one ignore the interior vertices? Well, we need to use interior vertices, but the interior vertices are not counted as n taxa. So this is some kind of extra information we need to deal with. But no, they are not part of the initial data when we describe the distance between two vertices. Okay. All right, so here is one easy abstraction to be a tree matrix. So here is one of the simplest example of a tree with 4 leaves. Then where now you can compute these 3 values D13 plus D24, D14 plus D3, D23, and D12 plus D34. So if you compute these three numbers, then you can easily check that D13 is the length of this path, which is A plus C plus E. D24 is the length of this path, which is B plus E plus D. So if you add them together, then you will get this number, A plus B plus C plus D plus 2E. We can do the same thing for D14 plus D23. You can check that these two numbers are same. On the other hand, if you compute D12, which is A plus B, and D34, which is C plus D, then this number is now different, and this is smaller than the other two numbers. Because when we compute D13 plus D24, we need to add E twice. So this is true for any choice of four vertices, four leaves on our tree with n leaves. So this provides a 4-point condition for any four subset ijkl in the set of leaves. We need to compute these three numbers. Then the maximum of these three numbers is achieved at least twice. So well, unfortunately, this is not in the classical sense an algebraic condition, because it is dealing with the condition that the maximum achieved twice. But anyway, this is really a relatively easy condition that we can compute easily. And indeed, this 4-point condition is the only obstruction for to be a tree metric. So the theorem of Bunemann in 71 is that a matrix vector is a tree metric if and only if the vector W satisfied 4-point conditions for any four subset ijkl of the set of leaves. Furthermore, in this case, the tree G is unique. Okay, let me pause a little bit here. Do you have any question? Okay, well, if you don't have any question, then please say no. So this is something I always ask to my students. Please say no. Okay, good. All right, so well, let me then move to algebraic geometry. So the first part was purely combinatorial. So here, let me introduce some basic notion of tropical geometry. Today, the tropical geometry I'm gonna use is very, in some sense, very limited, traditional, and an elementary part of tropical geometry. So let's fix on algebraically closed field K, and there is no restriction on the characteristic. If we have any Laurent polynomial F with n variables, then we can define the tropicalization of the tropicalized polynomial as a map from R to the n to R, which is defined as for any vector W, the tropicalization is the maximum of this inner product, U dot W. Okay, so we are going to take the maximum for the monomial whose coefficient is non-zero, so then there are finitely many numbers, so the maximum exists always. Then the tropical hypersurface is defined as the set of W's such that the graph of the tropical polynomial is not smooth, in the sense that the maximum in the tropical trope of F is achieved at least twice. So we have many linear maps. So the graph of tropical polynomial is we have many linear maps. We are gonna take the maximum of them. So this is piecewise linear. So the tropical hypersurface is the collection of a point where the piecewise linear graph is not linear. Okay. Then where we can define the tropical variety in this way. So then let's take any projective variety x in Pn-1. Then x circle is the, first of all, we are going to take the affinization, affine cone of x, which is in k to the n. We are going to take the intersection with the torus k star to the n. So this is a variety in a torus. Then this variety is defined by an ideal I in the Laurent polynomial ring. Then the tropicalization trop of x circle is the intersection of all tropical hypersurfaces where f is in the ideal I. Okay. Well, then it is a well-known fact that this is indeed, it has a fan structure in R to the n, and this is the dimension of the fan is equal to the dimension of x circle. Okay. All right, so here is one quick example. So now let's think about the tropical Grassmannian. So the Grassmannian Rn, by using the Flicker embedding, this is a subvariety of p to the n to the r minus 1. Then by using our recipe, we can describe the tropicalization of the Grassmannian, which is now a fan inside r to the n to the r. Then the idea of this Grassmannian is generated by three-term Flicker regulations, which can be described by using this formula. I mean, and knowing the precise formula is not important. So let me just say so. So here is one more concrete example. Let's think about the first non-trivial example, Grassmannian 2-4. This is a hypersurface defined by this polynomial, P1 to P3 4 minus blah, 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 which is in P5. Then the tropicalization of this polynomial f is now we have three terms here, here, and here. We need to compute the maximum of these three linear polynomials. And the tropicalized Grassmannian, which is in R36, is the set of all points Pij such that the maximum of these three terms is achieved at least twice. So well, if you want to do, then you can describe it in a very explicit way. But one thing I want to point out here is that the condition for tropicalized Grassmannian 2-4, which is the set of points such that the maximum of three linear polynomials is achieved at least twice. This is exactly the 4-point condition I explained in the first part of the lecture. The only difference is that at that time we used the distance vector, so Dij was always positive, but here Pij may be negative, so there is no sign condition. That's the only difference. Okay, so to fill the difference, so here is our definition of phylogenetic tree. So on n-leaf phylogenetic tree is a pair G, L, where G is a tree with n leaves, and L is the edge length function. But we want to extend the definition a little bit in the sense that all internal edges may have a positive or zero length, but all edges adjacent to leaves, they may have even negative length. Okay, so here is one example. So these three edges here, here, and here, they are internal edges. They must be n-least 0. We are going to allow 0. And the edges adjacent to boundary, they may have some negative edges. We are going to allow it. Okay. Well, one advantage to allow some negative value or even 0 value is the following. So first of all, if we fix the topological tree T, then the set of all edge lengths satisfying the second condition has a construct, which is R to the n, which corresponds to R boundary edges. And we have a product of the number of edges minus n, which is the number of internal edges. The number of internal edges product of non-negative real numbers, because we have those internal edges. So it parameterized all possible edge lengths satisfying the prescribed condition. So we have a closed cone, and where identifying trees have length 0 edge, with tree contracting the length 0 edge makes a way to glue several different cones together. So for instance, here on the left example, we have one edge with 0 length. Then we can contract this edge. Then we have another tree with a slightly different topology. So we have two different cones parameterized. The first kind of tree and the second kind of tree. We can glue these two cones together. So we can systematically glue many different cones together. So we can make an abstract fan here. This fan is called the space of phylogenetic trees. So here is one down-to-earth example in the case of T4. In T4, we have 4 different possible topology of trees. And this central one has 0 internal edges and 4 boundary edges. So it parameterized, the parameterization is R4. And we have 3 copies of 5-dimensional cones, which has 1 internal edge times 4 boundary edges. So they are 5-dimensional cones. So by gluing these 4 cones together, we can obtain T4. Okay. Well, then the theorem of, this is indeed one of the earliest papers in tropical geometry. The theorem of Speyer and Stumfeld, saying that the tropical Grassmannian trop GR2n coincide with the space of phylogenetic trees. So as a summary, if we combine tree matrix theorem and Speyer-Stumfeld's result, then they imply that we can define the dissimilarity map starting from the space of phylogenetic trees. So we have a matrix tree. Then we can define the distance vector. Well, first of all, this is injective by tree matrix theorem. Secondly, the image is exactly the tropical variety, which is the tropicalization of Grassmannian 2S. So there is a very interesting connection between combinatorics and tropical geometry. Okay, let me pause once again. Do you have any questions?
All good here. I don't know if you can see me when I move my head and say no, all is good.
All right, okay. Now let me move on. Okay. And now, so this is not the end of the story. So it was motivated by a question, reducing the size of noise. Well, if we apply this idea in the real world application, like computational biology, then we need to deal with the problem is more complicated because the practical data is always not accurate. We have to deal with the noise. But there were people in computational biology want to find some way to reduce the size of noise in the input data. So the question was one of the motivation of Pachter and Speyer defined higher dissimilarity map. So instead of using the distance between 2 taxa, so now let's think about the phylogenetic tree GL, and we are going to construct another set of input data in the following way. We are going to fix a number R. Then for any R subset in the set of leaves I, so this is a subset of the set of leaves, then we can define a subtree generated by this subset of leaves. So for instance, when we take a subset of 1, 4, 5, 6 in the 7 leaves in this example. Then here are 4 leaves, 1, 4, 5, 6. Then there is a unique tree connecting, spanned by these 4 leaves. Then now we can measure the size of this subtree H by just counting the sum, computing the sum of all edge lengths lying on this red subtree. So this is called D sub 1456, which is sum of all lengths, which is 15 in this example. Is it clear? Okay, then where instead of using the data measuring the distance between two taxa, now here is a new definition of R dissimilarity map. So for a tree graph, we are going to collect all of the size of subtrees. So this is a vector in R, n choose R. So we need to compute the size of the subtree for all I, all subset I in n whose size is exactly R. Okay, well then we can make a bunch of numbers, positive bunch of numbers, and you can check that when R is 2, then this is exactly the ordinary dissimilarity map. Then where the question is, can we recover the graph, the tree graph GL, the phylogenetic tree, from this new data R similarity, the image of R similarity map? So the answer of Pachter and Speyer is that if the size of R is relatively small with respect to compared to the number of leaves, then this R similarity map is indeed injective, which means we can recover the original tree uniquely. Okay, so well, this is a good news. And in the same paper, Pachter and Speyer asked 2 important questions. The first question is that, interestingly, it seems that the image of this R dissimilarity map, DR, is contained in the tropicalized Grassmannian. So the question is it true or not? The second question, well, you may wonder that if the image of DR is equal to the tropical Grassmannian, because it was true when R is 2, but because of some obvious reason, their dimensions are different. So this is not true. So one can expect that the image of DR is contained in the tropical Grassmannian. That was one question. The second question is the image of the R dissimilarity map a tropical variety or not? If it is a tropical variety, then it is a very tempting question to find the ordinary variety X whose tropicalization is equal to image of R dissimilarity map. Okay, well, there have been progress. For the first question, it has been proved by many different people by using many different methods. For instance, Kurz and Iriarte Girardo, they proved it by using some combinatorial argument, and Chris Manon used some representation theory. However, for the second question, can we describe the image by using a tropical variety and find the variety X? There have been very limited progress. The suggestion of Pachter and Speyer in the same paper is that, well, we already know that the tropicalization of Grassmannian 2n is the space of phylogenetic trees. So how about to find the relational map from Grassmannian 2n to Grassmannian Rn and take the tropicalization of this relational map, and maybe the image of DR is equal to the image of this tropicalized map. So this is a very natural suggestion, and it was indeed successful when R is exactly 3. And they described the relational map, which is obtained by this identification. There is another. It is not surprising that Pachter-Speyer theorem is not symmetric. So on the chat, there was one question. Is it not surprising that Pachter-Speyer theorem is not symmetric with respect to the interchanging R and N minus R? Yeah, this is really, I mean, I know the proof, and the proof, indeed, the theorem, the result of the theorem is not true when R is larger than N plus 1/2. But it is really, indeed, it is a really interesting question to understand why. So now let's come back to this question later. Thank you. Okay, let me pause here again. Do you have any quick question here? Okay, well, please tell me if you have any question, okay? I don't want to rush. Okay, so first of all, let me explain something about our result in the second question. So the second question was, is the image of the R similarity map is a tropical variety or not? So surprisingly, the question is really elementary, but the people couldn't find the right candidate of the variety X. The reason is simple, because the image of R similarity map is not a tropical variety. So here is the idea of the proof. So we calculated the simplest non-trivial example. R is 4 and N is 7. In this case, the tropical, in general, a tropical variety is a balanced fan. So I'm not going to explain the definition of a balanced fan, but here is a one-dimensional example. If we draw a tropical variety, one-dimensional tropical variety, then locally it looks like this one. So we can find 3 vectors spanning 3 different cones. Then where these 3 vectors are never linearly independent, right? So if we have a higher dimensional cone, then you can find the ray generators of the cone. Then the ray generators always had some sort of linear dependence condition. But in our example, image of D4, we explicitly calculated the 13 edges from the 4 cones on the picture. So we have 4 different cones describing the metric trees with the given topology. But there are 13 edges. We calculated their linear dependence. They are linearly independent. So this is not a balanced fan, which means it cannot be a tropical variety. All right, this is the bad news, but what I want to say is that this is not too bad. We can modify the definition of the dissimilarity map slightly, then we can make the right answer. Okay, so here is the definition of a modification of the dissimilarity map we introduced before. So suppose that we have a metric tree, fix R, and take a subset I of the set of leaves. Then now, so here is an example of 1, 4, 5, 6. Then we can describe a subtree spanned by these 4 leaves. So in the definition of ordinary dissimilarity map, the way to measure the size of this subtree is simply take the sum of the length, edge length on this tree. However, instead of doing that, now we are going to take every pair of vertices lying on this subtree, and we are going to compute the pairwise distance, and we are going to add them together. So in this subtree, we have 4 vertices. So there are 4 different paths connecting 2 of them. So our definition of the weighted dissimilarity is that we are going to add the pairwise distance of any two pair of vertices of leaves in the subtree. Then we can compute the length of each path, take the sum, then we will get a different number. Okay. So is it clear the difference between the original dissimilarity and our weighted version? Well, one thing you can easily check is that when the size of the subset I is 2, then this is equal to the ordinary distance, obvious. When the size of I is 3, then the weighted version is 2 times the non-weighted version. But when R is greater than or equal to 4, then the vector we can obtain by using weighted dissimilarity and the ordinary dissimilarity, they are not parallel. They are not scalar multiple of each other. Okay, so now we can make a weighted variant of the dissimilarity map. So instead of using DIs, so this is the definition of DR. So we are not going to use this one. Instead of that, we are going to use the weighted variation of the dissimilarity vector. Okay, then now my claim is that this is in many different regions. This is, it behaves very well. First of all, this map is, it can be decomposed as a composition of two maps. The first one is the ordinary dissimilarity map, D2. And the second one is a linear map from R to the n choose 2 to R to the n choose R. And indeed, we can compute the linear map very explicitly. So from xij vector, we need to map this xij vector to n choose R dimensional vector, whose each component parameterized by an R set I. This is simply sum of coordinates. So in other words, the matrix of representation for LR is simply 1-0 matrix, which means very combinatorial. Furthermore, this is not the end of the story. This map LR, the linear map LR, which is a 0-1 matrix, is indeed a tropicalization of a morphism Pr, where Pr is a morphism between two tori induced from the following map. So for the coordinate Pi, we can simply send the product of Pij where Ij is in I. And this is a very combinatorial map between two Laurent polynomials. Take the associated map between affine varieties and take the tropicalization of the map, then we can obtain the linear map error. So there is a connection between the linear map and the tropical variety. Okay, so here is the algebra morphism between two Laurent polynomial rings. Furthermore, so we have a map here from one torus to another torus. For the first torus, we have the Grassmannian. The Grassmannian is embedded into this torus. And for the second torus, the larger Grassmannian Rn is embedded. Moreover, this map Pr factors through this direction. In other words, if we restrict Pr to the Grassmannian 2n, then the image of Pr restricted to Grassmannian 2n is contained in Grassmannian Rn. So in some sense, we can make a map from Grassmannian 2n, rational map from Grassmannian 2n to Grassmannian Rn. Moreover, the map is induced from this very natural Veronese Grassmannian map from Grassmannian 2n to Grassmannian Rn. So you can see that you can see the way to describe the map. So for each column, so we can describe the Grassmannian by using 2x(n) matrix. So take one vector and take the Veronese embedding of this two-dimensional vector into R-dimensional vector space. then perform the same operation column-wise. Then this map is not well defined on Grassmannian 2n to Grassmannian Rn because of the length condition. However, if we restrict it to Grassmannian 2n circle, which means all of the Flickr coordinates are non-zero, then this map is a well-defined regular map. Okay, and indeed this map is coincide with the map PR described here. The reason is that if we take any minor R by R minor of this image matrix, then this is a homogenized van der Monde matrix. We already know how to compute the determinant of a van der Monde matrix, which is the product of yi minus yj. If we homogenize it again, then this is exactly the product of determinants of minus here, which is exactly the product of Pij. Okay. So where the image in Grassmannian Rn is the set of R-dimensional vector spaces, which can be represented of this form. And now, instead of thinking it as an R-dimensional vector space, subvector space in n-dimensional vector space, let's take the n columns. Then for each column, describe a point in PR minus 1. So we have n tuples of R minus 1 dimension points on R minus 1 dimensional projective space. So we have a point configuration. Moreover, this point configuration, each point configuration is, as you can see, this is in a standard rational normal curve. So if we describe VR minus 1n as the set of all endpoint configurations lie on a rational normal curve, then this variety VR minus 1n has a connection with the image of the tropical Grassmannian 2n and via the Gelfand-McPherson correspondence. So I'm not going to explain the detail of Gelfand-McPherson correspondence here, but you can understand it in this way. They are different varieties. They have different dimension. They have different nature. However, the defining equations of VR minus 1n and the defining equations of the image of Grassmannian 2n, they can be identified. Okay. Okay, so here is the summary. The image TRN, so I will denote the image of the weighted dissimilarity map by TRN. It can be realized in two equivalent ways. First of all, this is the tropicalization of the map PR of Grassmannian 2n. Or equivalently, we are going to use the second point of view intensively. The tropicalization of the Gelfand-McPherson correspondence of the locally closed subvariety VR minus 1 inside PR minus 1n, which parameterize the point configurations lie on a rational normal curve. Okay, so the second one is obtained by applying Gelfand-McPherson correspondence, which is equivalent to the first one. And moreover, we proved the following theorem as well. So in the weighted variance, so as Dmitry asked the question, so it was very curious why the symmetry wasn't there. In our result, the symmetry is there for any number R between 2 and n minus 2. This weighted dissimilarity map is indeed injective. And the proof is really simple. So we know that the weighted dissimilarity map is a composition of two maps. And the first map is already a bijection. We have it is sufficient to check the injectivity of the second one. This is a linear map, indeed a 0-1 matrix. So we can compute the pseudo inverse of this linear map explicitly. This is a really combinatorial computation. Okay, let me pause a little bit again. Do you have any question? Okay, so now let's move to the second part of the story. I personally believe that this part is really more interesting. So one of our original questions is the following. In our new setup, suppose that we have a vector W in R to the n choose R. So the question is W in the image of the weighted dissimilarity map? If this is true, then we know that there is a unique phylogenetic tree inducing this weighted dissimilarity vector. Our focus is the next question. Is there any simple algebraic criteria? Okay. Well, so we know that the image of the weighted dissimilarity map is equal to the tropicalization of technically the Gelfand-Mapperson correspondence of Vr-1n. But as I told you before, the defining equation of Vr-1n and its Gelfand-Mapperson correspondence has natural correspondence. So it is sufficient to find the defining equation of Vr-1n as a subvariety of Pr-1 to the n. So now the question is, now we want to find finitely many equations fi defining Vr-1n such that the tropicalization of Vr-1n is equal to the intersection of the tropicalized hypersurfaces. Well, because we already have three-term Flicker relations, we know that the image of Vr-1n is contained in the Grassmannian Rn. The Flicker relations does define Vr-1n. So the question is, what other equations should we use? I mean, so the Flicker relations are part of the defining equations. We need to find more equations. Okay. So let's start from the simplest non-trivial case, the equation of V26. V26 is the subvariety of P26, which parameterizes an open-dense subset of the point configuration 6 points lying on a smooth cone. Then this is very classical result in 19th century that this subset is this is an open-dense subset of an irreducible hypersurface defined by this polynomial. But one interesting observation is that the equation is not fully S6 symmetric. On the other hand, by the definition, V26 is obviously S6 symmetric. The reason is the Flicker coordinates had many relations between them. So for the same polynomial, same function, we can find many different presentations. In our work, indeed, we need to use different presentations. So here is a way to describe all different presentations. So now let's take a graph G whose vertex set is the set of 3 subsets of 6. So here are several examples. They are vertices. And we are going to connect 2 vertices if and only if their intersection is of side 2. So 1, 2, 6 and 2, 3, 6 has the share 2 entries, 2 and 6. So we are going to connect them. So this is a 3 regular graph with 6 to 3 vertices. Then now we are going to take a subgraph of this graph G, which is isomorphic to a 3-dimensional cube. So this is one example. So this is an example of a cube C. Then we know that any cube is a bipartite graph. So we can separate the set of vertices into 2 disjoint sets. So the one is the set of blue vertices, the other one is the set of red vertices. Then whenever we have this bipartite structure on a cube inside the graph G, then we can describe another form of defining equations, which is the difference of 2 monomials the first monomial is the product of all Plica coordinates corresponding to the blue vortex. And the other one is the product of Plica coordinates with respect to red vortices. So then one concrete example from this cube is that the first term is the product of blue vortices, P125, P146, etc., etc. The other one is from red vortices. Okay, this is purely combinatorial, and this is one of the examples of this construction. It is a good exercise to find a cube which provides this presentation. So our key ingredient is to apply Gale transform to compute the equation of VR minus 1n for higher R and higher n. So here is the definition of Gale transform. So now let's take a full-length R by n matrix A. Then by taking the column vectors, we can make a point configuration in P to the R minus 1. So we are going to denote it by PA. Then the Gale transform, G of A of the matrix A is another matrix B, which is a full-length matrix of size n minus R times n, such that A times B transpose is the zero matrix. And so you can think that this is finding the orthogonal subspace. Okay. Well, then first of all, G of A is clearly not well defined, but it is well defined up to general linear group action. So there is some ambiguity. But anyway, here are three important facts we are going to use in our proof. First of all, the Gale transform is involutive up to GL action. This is easy. Number two, this is somewhat surprising. Up to a scalar multiple, if you have a matrix, then you can compute the determinant of minor as a Plica coordinate. There is a correspondence between the Plica coordinate of the original matrix and the Plica coordinate of a Gale transform. If you take the complementary index, then the determinant of the minor of the complementary index of the Gale transform is equal to the original one, up to a scalar multiple, but this scalar is independent of the choice of I. Okay, so this is somewhat surprising because the A and the Gale transform, their size are different, but we have such a connection. And finally, this is a classical result of Koebler in 1922. The original point configuration is on a rational normal curve if and only if a Gale transform is on a rational normal curve in a different projective space. So we are going to use these three facts to construct many equations to define VR minus 1n. Okay, here is the recipe. So we are going to start from a point configuration PA. For any subset I of the index set, PA sub I is the sub-configuration of a point parameter indexed by the subset I. Then let's start from a point configuration in PR minus 1n. This is an n point configuration on PR minus 1, which lies on a rational normal curve. We are going to forget, by restricting the index set, we are going to forget some points. Then still it is in a rational normal curve. Take the Gale transform, then it is a rational normal curve, but by the numerical region, this is in a rational normal curve in two-dimensional projective space, which is a cone. We are going to further restrict the point configurations by taking a sub index set J. Then this is in V26, we already know that for V26, the defining equation is of this form. We need to choose a cube C on the set J, but the defining equation is of this form. Difference of two monomials. Then now we are going to backward. If we forget J, then that means we are going to take the pullback. Then still the defining equation, the same defining equation hold. We are going to take the Gale transform. Then if you take the Gale transform twice, then the Gale transform, and this is the original point configuration. So we do have a recipe connecting the empirical coordinate of the original point configuration and the Gale transform. So that we have these kinds of defining equations. Finally, removing the index set, we can take a pullback, then it satisfies the original point configuration, satisfies the same equation. Well, so by using this recipe, by combining several algebraic geometric properties of Gale transform, we can make many defining equations of this form. And our result is that any non-degenerate point configuration in the product of projective spaces is in VR-1n if and only if it satisfies these kinds of equations from cubic for all I, all j, and all q's. So we are almost done. So we know that we can cook up many defining equations of this form, right? One important thing is this is a binomial. This is a sum of two monomials. So if we take the tropicalization of this equation, this is really simple, which is the maximum of these two sums. Okay, there are only two terms. We need to compare the maximum of the first one and the second one. So if you compute the tropical hypersurface correspond to this tropicalization, then the maximum must be achieved twice. So these two terms must be same. So the tropicalized hypersurface is the linear equation saying that the first one is equal to the second one. So therefore, if you take the intersection of all tropical hypersurfaces of this form, then this is a linear subset or subvector space of R to the n choose 2 by using a highly non-trivial combinatorics. We could show that this is equal to the span of the image of the weighted dissimilarity vectors. Okay, which is isomorphic to R to the n choose 2. Then finally, after that, we have political relations, three-term political relations defining the tropical Grassmannian. We can pull back all of them to this subvector space, which is isomorphic to R to the n choose 2. And the pullback of political relations are political relations. So they define the tropical Grassmannian GR2n. Okay, so this is the idea. So as a result, we can make the following very nice criterion. A vector W is in the image of the weighted dissimilarity maps, if and only if it satisfies two different kinds of defining equations. The first one is the three-term political relations. And the second one is the linear equation from cubics. Okay, I'm sorry. I need to replace the three-term political relations. No, this is wrong, sorry. The tropicalized one. In other words, 4-point condition. I'm sorry. So it satisfies the 4-point condition, which is the tropicalized three-term political relations. And it must satisfy the linear equations from cubic. Okay. So the two key remarks. First of all, the space TRN, the image, and the set of equations are characteristic independent. There is absolutely no role of the characteristic of the base field. On the other hand, it is well known that the tropical Grassmannian is dependent when R is n with 3. And if you really want to do some practical computation, then we don't need to use all written relations in linear equations. We can use only n to the 4 above Flickr relations and n to the r minus n to the 2 linear equations. They are sufficient. So in other words, there is an abundancy of the defining equations. But these equations are really easy to check. So I think the image of the weighted similarity map is a really interesting and helpful creature. Okay, I'm gonna stop here. Thank you very much and happy holidays.
Thank you. Okay, we have some time for questions. Any questions from the audience? You can write on the chat if you want me to ask it for you. Okay,
I have a very minor remark in case.
Go ahead.
Han-Bom, in your slide 28, the attribution should be to Goppa, not Coble, the very bottom for the...
Really?
Is it a result of Goppa related to coding theory?
Oh, baby, yeah. Thank you. Thank you for pointing out. Yeah, okay. I need to change it. And then let me double check. Thank you.
Almost 100 years old.
But still, you know.
Okay. Any other questions? Can you go back to the slide where you talked about the characteristic towards the end? No, towards the end.
Okay.
So I'm shocked about that. I thought tropicalizations only made sense over, over the reals for varieties that come from complex.
Well, we can define it on arbitrary algebraically closed field. Even algebraic closedness condition is not really essential.
Right, that's interesting.
We can define it, but in different fields. In any case, the target is Rn, right?
Yeah, no,
but
that's
the initial variety can be defined on the many different fields.
Right. Okay. All right. Any other questions? No. Well, thank you very much, Han-Bom.
Thank you.
It's been a pleasure to see you again.